channel where you, me, and my houseplants are going to have some fun doing math. So today we're going to start by saying, what is a limit? So we often write out that the limit as x goes to a of f of x is equal to what? A number, does not exist, something. So what does that mean? Well, if we look at this first graph I have here, we'll say that this is y equals f of x. And let's choose a value to be our a. So let's say a is right here. Then we can talk about the limit of my function f as x goes to a, either from the left-hand side or the right-hand side. So if I say the limit as x goes to a from the left of f of x, then I mean I want to travel along that function from the left, taking values of x closer and closer to a. So my x values are approaching a, and I'm traveling along the function. So in this case, I'm going to end up near some value, let's call it b. If I do the same thing from the other side, so if I want to look at the limit as I approach from the right, let's pick a new color, then I'm taking values of x getting closer and closer to a from the right, so I'm taking smaller and smaller values, and I'm traveling along my curve from the right. So in this case, I would have the limit as x goes to a from the right of f of x, and we notice as we travel along, we're going to meet up with those green arrows, and either way we go, we're approaching the value of b. And so we say, because the limit from the right and the limit from the left agree, they're equal, we say that the limit of this function at that point as x goes towards a is actually going to be equal to b. So I'll write out what I just said there. So since the limit of f of x as x goes to a from the left is equal to the limit of f of x as x goes to a from the right, which is equal to some value b, we say that the limit of f of x as x goes to a is equal to b. So when I said that the two had to agree for the limit to exist, that implies that sometimes the limit does not exist. So let's look at an example of when that happens. In this graph, again, I'm going to call it y equals f of x. This time we will set a to be 1, because that's where something interesting is happening. So if I travel along my graph from the left, taking x values approaching 1, I notice that my function value, or my y value, is actually staying the same at 1/2. But as I go from the right, well, as I take values of x larger than 1 but getting closer to 1, so maybe I start with 4 and then 3 and then 2 and then 1.5, and I get closer and closer, I'm traveling along this curve, and I notice that my values are changing and they're approaching some value here. Let's say it's approximately 1.9. So traveling from the right, I get a value of 1.9. So notice that these two do not agree. So we can say that since the limits are not the same, the limit as x goes to 1, we say here, does not exist. An interesting thing about this example is if you look at f of 1, if we evaluate this function at x equals 1, well, what do we get? Well, we have an open circle when we go from the left, and we have an open circle when we go from the right, so actually it's undefined. But that didn't matter when we were finding the limit. So Even though our function doesn't actually even exist at that point, that's not what caused our limit to not exist. So an important thing to note about limits is that the limits only matter around the point. So we're looking at the behavior of the function near some value x equals a, but we don't actually care what happens at x equals a. So let's look at an example where we have the same thing where something's not defined at a value, but the limit still exists. Here we'll set a equal to 1 once again, and we'll take the limit as x goes to 1 from the left. So we travel along our function on the left, approaching 1, taking values of x larger and larger until we get closer to 1. We're coming up to, again, let's say this is 1.9 again. And as I approach from the right, I take values of x that are smaller and smaller, getting closer to 1. I follow the curve and I get the same value once again. You see they're lining up even though there is a hole there. But the closer and closer I get, that hole is infinitely small. So I can get as close to that hole as I want without actually falling into it, unless I choose x to be a, which we're not going to do. And so because they agree, we say that the limit as x goes to 1 of this function is equal to 1.9. Even though my function is undefined there. And so this is really powerful because it means that we can talk about the behavior of a function very, very near a point where we can't talk about the function actually existing. Here we've looked at a quick introduction of how we can look at limits and how we can talk about them. In the next few videos, we'll look at using limits to discuss functions, but also using limits specifically to talk about the continuity of a function. So we say that a function is discontinuous, or just that it's not continuous, if you have to pick up your pen to draw it. Now that's a very hand-wavy definition, and so we're going to look at how we can use limits to more properly define discontinuity and what it means for a function to be continuous. And we'll also look at how we can actually compute limits without just looking at the graph. So join me for that.